please.
Thank you very much. I would like to introduce to the kind public a method to estimate direct functional connectivity, which is based on Granger causality. And when you want to estimate direct functional connectivity, basically there are two methods. Okay, thank you. Okay. I was saying dynamic causal modeling is one of them, and the other one is Granger causality. And I would say that they sit at opposite extremes of the spectrum of the tools that that are available for effective connectivity, because dynamic causal modeling, it's so specific. It's heavily based on a physiologically inspired model, and then on top of it, there are task activation. You need to define the paradigm. There is a model for interaction, so it's very much hypothesis-driven. On the opposite side of the spectrum, Granger causality is totally general, is even application agnostic. No task, no paradigm, good for resting state, give the signal, push the button, it works. Period. Obviously, you get what you pay for, because in case of dynamic causal modeling, you get exact answer to your very specific questions. While on Granger causality, you don't get answer, you just got some hints. And these hints would represent the starting point of the physiological hypothesis. And Granger causality is so general because basically it is based on two assumptions which are very general. The cause happens before the effect, and the cause contains some unique information about the future of the effect. I will give you an example. In 9 minutes time, I will say that in humans, the fault mode network is causal on Salient's network. But this just means that in Granger sense, there is something in the signal distilled from the fault mode network which let us make better prediction on the system coming from Salience. So after this caveat, let's see how we do it. If we say that Z is causal on X, if there are some information, we should be evaluated somewhat with a model. So we try to make the best prediction you can on X without Z, and this is called a restricted model. And then we take another model where we take into account information coming from Z. And then we check for residuals if the second model is statistically better represent the future of X. If yes, then Z is causal on X. Granger causality is very general. However, it's based usually, classically employed, it's based on a linear model, the autoregressive model, which has some limits, of course. So the question is, I would like to do it possibly non-linear, more adaptive to just everything. So for example, speaking about fMRI, I can put some details inside those question marks of the physiological details of the models, but this is not what I want to do, otherwise the Granger causality would not be general anymore. So I need to find a way to represent the output in a possibly non-linear way with the input. And today, usually we do it with artificial neural networks because they are so flexible. And if you don't have idea of how possibly non-linear deep neural networks can get, play with the playground at TensorFlow just to get an idea of how complex the system. How complexly the system can represent your output. With great flexibility comes the cost of a huge amount of parameters, so we take the risk of running into troubles very quickly because then the system would be over-parameterized. So we make use of a special class of artificial neural network which are non-trainable, which are termed echo-state networks. So you take a bunch of neurons, you connect them at random with fixed weight, which you don't train, and then you just search in the space of the states of the network some information that helps you to predict the output. And in this way, you have no training, there's no overfitting, it's very computationally effective, and we built our model, our tools based on that. You can look at the mathematical details in the paper, which we just published on bioRxiv. By the way, it's very easy to implement, computationally speaking. So if you don't want to do it, check it out on my GitHub page. But obviously, we want to compare the performance of these new tools with some very well-established tools, which are, one of them is the state space Granger causality, another one is the kernel method Granger causality. To detect the performance, basically we have to generate our ground truth. So first we generate a complex networks with links. These networks represent our ground truth. We want to detect those links. On every node of the network, we generate some complex dynamics, which is based on Duffy oscillator because it's nonlinear, possibly chaotic, possibly synchronizable depending on parameters, and it has many features you can play with. And so from the signal that we get, we feed our machine, and then we want to see if we can reconstruct every single directed link of the network. And we evaluate performance with the receiver operating characteristic curve. So let's take a ground truth network with average density and very weak coupling. The classical autoregressive Granger causality, as you see here, performs very poorly, basically shunts level. But kernel-based Granger causality, which has been designed by Marinazzo et al. Some 10 years ago, performs much better because it was designed to be nonlinear. But nowadays we have state space Granger causality, which has been introduced a few years ago by Barnett and Seth, and it performs even marginally better. Our echo-state Granger causality performs even better. Simply that. And the area under the ROC curve is always marginally better without respect of the density of the network, of the coupling strength of the network. So substantially echo-state Granger causality vastly outperform state-of-the-art Granger causality tools, even if you consider the positive predictive value of the 10% most connected, you have a positive predicting value which is quickly squeezed against 1. So if you want just to consider what is the most obvious link that you get, most probably is going to be a true positive. And so finally, the application, we apply these tools as an example to within network directed connectivity, because there is taken from the Human Connectome project because of the quality substantially. It's resting state, and basically because these networks, they have some link with a physiological meaning. And so down to the results, basically averaging the estimated network of each single subject and averaging all the networks subject-wise, we get some hints. Granger causality gives us some hints, for example, tell us that the default mode network is causal on salience, that secondary visual is causal on some other visual networks. Interesting, I find it interesting that motor limbic network precedes temporally the cerebellar, so like mind precedes motor action. And well, to conclude, substantially, We presented we presented a method. The method works, has been validated, and we show an application to between network directed connectivity. Thank you very much.